In the last class, we saw all about temperatures, right? And then we saw thermal expansion. So these are all thermal phenomena. So temperatures, you know clearly the difference between heat and temperature. We will be doing more about heat later on. And then we saw thermal expansion, how, you know, providing heat to a substance can change its length, area, and volume. We saw that part of it. And now we'll look into the kinetic theory of gases. And I just started talking about Brownian motion. So what did Brown observe? He had a smoke cell. The smoke cell, basically, there are smoke particles in it. You know, just smoke and then push the smoke into that smoke cell, and that's it. You have smoke. And then put light from this side and use a microscope and look from above, and you'll see the smoke particles. They are actually smoke particles. And the smoke particles will be seen to be moving, and they'll be seen as specks of light because of the light there. And what Brown observed was this, that the smoke particles were seen to be going in straight lines, and suddenly they change directions completely randomly. And then sometimes they seem to be going faster, and sometimes they go unaffected for quite some distance. And then after that they change directions, and again change directions, and change directions, and there is no order at all as to what is happening and how it's supposed to be happening. So this is what Brown observed, completely random motion. Couple of things that he observed. One, they were moving in straight lines. Okay? One, they're moving in straight lines. Second, they were moving at different speeds. Different velocities. And random. What did you conclude from this observation? What he concluded from this observation is that, first of all, why are they changing directions? They're changing directions because they got bumped into by atoms of the air. Yeah.
Are the atoms of the air like relatively stagnant and they're coming and bouncing off of those, or are they both colliding into each other? Like, are the atoms of the air also moving?
Oh, the atoms of the air are moving really fast.
As fast as in smoke?
Oh yeah. Smoke particles are pretty heavy. Compared to the atoms, smoke particles are very heavy. That's the other observation he did. He saw that the smoke particles were moving slowly. They were not moving really fast. Haven't you seen dust particles in, when bright light comes into the room, you'll see dust particles moving like that? Right? That's basically what it is. That's Brownian motion. If you observe the dust particles very carefully, you'll see how they're changing directions pretty randomly. That is basically Brownian motion. But when you normally see dust particles, you don't see one. You see a lot of them, so you don't really focus on one of them. Right? But if you can focus on one of them, you see that they're moving slowly. Why are they moving slowly? And why they change directions is because they get bumped into by atoms. So many things can be understood here. One, atoms are moving fast. Because atoms are light, they should be moving fast in order to cause a change of momentum to this smoke particle, right? So if the heavy smoke particle is going to get deflected by a lighter particle, that means definitely that must be going fast. Okay? If you are running like this, and if a bullet comes and hits you from here, and if the bullet has enough momentum, your direction will change because of the momentum of the bullet. I mean, if it is really fast, you will be changing. You won't be going in a straight line. You'll get deflected. Same with any sport. If something is coming really fast, you'll definitely be changing your path. All right. So straight lines. Why straight lines is because, okay, there's a collision over here, and then the other collision is taking place after a long time. What's happening in between? No collisions at all. What is understood from there? That the interatomic space in gases is pretty large. That means the atoms are kind of here and there. So it's very less likely to get hit. You understand? It is less likely to get hit by an atom because atoms are pretty less dense. I mean, like the air is less dense, which means the atoms are kind of scattered here and there. And yes, the atoms are moving, but how likely is it to come and bump into this smoke particle? Less likely, because the interatomic spacing is large. So going in straight lines, you understand, it is like soccer. Soccer. Players are not everywhere, right? One player is here, the other player is there, the other player is there. And now the ball is going between player to player. Is it approximately going in straight lines? From one player to another player, it is going in straight lines, right? Because after it gets kicked by one player, nobody is touching it. So it keeps going straight. It goes straight until another player deflects it. So now imagine the whole football, the whole soccer field is full of students. Full of students, packed. And then you push a soccer ball under their feet. How do you think the soccer ball is going to go? Like it'll be like changing directions very soon. It is not going to go in straight lines at all. It will be just like that. And that is how particles move in a fluid. And not, in a liquid. Because in liquid, if you put a little dust particle in liquid, you will see the dust particle is not going to go in a straight line. It's going to go like curvy, right? Why is it getting curved? Why is it a curved motion? Because in a liquid, the atoms are pretty close, so they get bumped into very often. Whereas in a gas, atoms are far apart, so between atoms, between atomic collisions, the smoke particle is seen to be going in straight lines. So what you understand from the straight lines is there's a lot of gap. Different velocities. The smoke particle is actually moving at different speeds, different velocities. After one collision, it's going fast. Next collision is going kind of slow. That implies that the atoms are moving at random speeds also. Not all the atoms are going at the same speed. Some atoms are literally not moving. Some atoms are going really fast. So the atoms have different speeds. That's what you understand from here. And the randomness of the direction tells you that the atoms are moving in random directions. So the atoms move in random directions. That's what Brown observed. Some of those things are going to be taken as our assumption too. So what are the assumptions of the kinetic theory? Assumptions of the kinetic theory of gases. We do take some number of assumptions to start off our discussion about kinetic theory. So what are we trying to achieve from this? We are trying to find out what exactly is causing the pressure in a gas. Okay? And can you get a quantitative measure of that pressure? And what factors does it depend on? These are the things that we're going to learn here in kinetic theory of gases. All right. To start with, the first assumption is something that we already know. That is, I'm not writing it down. You can write it down. Number one, atoms are moving in random directions at random velocities. Atoms are moving in random directions at random velocities. The interatomic distances are pretty large. You can take that as the next assumption. The interatomic distance is very large. Now, most of these things are observed by Brown. The interatomic distance is very large in gases. The atoms undergo elastic collisions. These are assumptions again. The atoms undergo elastic collisions with each other and the walls of the container. The atoms undergo elastic collisions with each other and the walls of the container. What do you mean by elastic collisions? No kinetic energy is lost. Yeah. No kinetic energy is lost. So if an atom goes and hits that wall and bounces back, it will come back with the same kinetic energy. So we saw last year inelastic collisions and elastic collisions. Elastic collision means kinetic energy is conserved. The total kinetic energy of all the atoms is not going anywhere. That's what it means. How many assumptions so far? Yeah.
Is the interatomic distances, which are very large, that's in relation to what?
That's actually to tell you that the interatomic forces are very weak. You can write that also down. The assumption, interatomic forces. Interatomic forces are negligible. Yes.
Well, there's the forces that hold them together. Is that what you're referring to?
That is the interatomic force, yes. In other words, in gases, the forces that hold the atoms together is negligible. It's not there. Unlike liquids and solids, there are forces holding them. In gases, the atoms are so far apart that the interatomic forces are negligible. Next assumption. Did I say a random part of it? Yes?
Yeah.
Next assumption is the atoms obey Newtonian mechanics. They obey, in other words, whatever you learned in Newton's laws, Newtonian mechanics, you learned about momentum, conservation of momentum, kinetic energy, and all those things. Everything applies to atoms as well. It's not a big assumption, but yes. So we are applying that. Next one. The volume occupied by atoms and molecules, the volume occupied by molecules or atoms is negligible compared to the volume of the gas. The volume occupied by the atoms or molecules is negligible compared to the volume occupied by the gas. What do you mean by that? Yeah.
Maybe that they're so spread out that like the area between them takes up is like way more than the actual particles.
The actual particles. Like for example, if I ask you a question just now, how much volume of air do you have in this room to breathe? How do you calculate? How do you measure that? How much volume of air do you have to breathe? So will you take length, width, and height? Is that it? Huh?
Percent of oxygen.
Huh?
Percent of oxygen.
No. I mean like totally air. I'm just talking about air. How much air do you have to? How much air do you have in this room for you to breathe? That's my question. So if you take length, width, and height, you're totally wrong. Length, width, and height, if you do that, it is for an empty room. Are you empty?
No.
Aren't you taking space here? So you're taking space, this table is taking space, the chairs are taking space. So all that space is already used up. There's no air over there. You understand? So basically, if you have to do that calculation, what you have to do is this. The entire volume, length, width, and height, minus all your volumes, minus the volume occupied by the tables and all those things in the room, then you'll get the right number. The actual amount of air that you have to breathe, that's what you should do. The same way, atoms in this room, if I have a container full of a gas, each atom or each molecule has how much volume to run around? The actual way of doing it is take the entire volume and subtract all the volumes of the atoms and molecules. Now, what we are saying here is the volume of the atoms and molecules are negligible compared to the volume of the room, which means each atom has the entire room. You understand what I'm saying? Right? Because the atoms are tiny and because they're spread out, they don't really occupy too much of a volume. And therefore, each atom has the entire room to move around. That's what it means from there. Yes, the volume occupied. Yes. The next assumption is this. The time of a collision is negligible compared to the time between collisions. Time of a collision is negligible compared to the time between collisions. These are all assumptions of kinetic theory of gases. The time of a collision is negligible compared to a time between collisions. Now, what does it mean? What it means is this. Look at it, just one atom. The atom is going and bumping into that wall, right? And then bouncing from there. And after bouncing from there, it goes all the way to the other wall and bounces from there. So what we are trying to say is, between two bounces, the time taken between those bounces is actually much larger than the time of that collision. So we're just ignoring the time the atoms are making contact with the wall. You understand? Because the other time is big, much bigger. And the last assumption we can say is there are many atoms. There are so many atoms so that statistics can be applied. See, statistics cannot be applied when there are just a couple of them, right? Like you can't just say, all right, let's see, Trinity, which color do you like the most? Okay, so if you want to do a survey of which color you like the most, you can't just like see 5 students, talking to each other and then say, all right, I want to interview you all. All right, which color do you like most? Green. Which one? White. Which one? Green. And then finally you'll say, all right, 60% of Trinity likes green and 40% likes white. Can you just conclude like that with a sample of 5?
No.
Never. A sample of 5 is not a good sample to come to a conclusion. You need to really do massive numbers. Unless you do a massive number, you cannot really take a proper measure. The same thing with, pre-polls, right? But before the elections, they're doing some polling and all those things. They're not doing a big sample over there. They're taking a smaller sample. And when they're doing that, that could be a false information. Because it could be right, but it all depends on the sample size. Anyway, so what we are trying to say is here, there are so many atoms in this room that you can just apply statistics pretty easily because there are lots. So you can generalize things. Okay? So these are the assumptions on which you are actually going to build this kinetic theory of gases. And now let's start working on it. So here is your container. So we have a container of, I'm taking it as a cube for convenience. I'm taking the container as a cube of side L. I'm taking it as a cube of side L. And you got to look into it a little three-dimensionally, okay? So that's why I'm drawing it this way, so you'll understand it. And in this container of side L, there are n number of atoms or molecules. Let's talk in terms of molecules. So there are n number of molecules. And all of them are moving in different directions at different velocities. They all have different velocities. Let's take one of those. We're just focusing on one of them right now. Okay, there's one atom here, or one molecule here, which is moving in a certain direction with the velocity c1. It's moving with the velocity c1. That's the velocity of the first molecule. Like that, there are so many, and the mass of the molecule is m. The mass of the molecule is m. And it's moving with a velocity c1. What exactly is happening to this molecule? It's going with a certain momentum. You know what's momentum, right? What's momentum? Mass times? So it's mc1, momentum. So it's going with a certain momentum, and it's going to bounce on a certain wall. It's going to bounce on a certain wall. Now, since it's going at a weird angle, it's going to bounce on a certain wall and then bounce off from there. So if you want to really study the momentum, changes of momentum that's going to go through, you cannot just go using mc1. You need to split it up into x, y, and z axis. So let's split this velocity c1 into three components. U1, V1, and W1. Those are three components. So the velocity c is probably like, look at this. Imagine this is the room, and here's a molecule going like that. Does this have an x component? Does it have a y component and a z component? So you can have, like x component, a y component, and a z component, which is whichever way it is. You can see it from here. So there is an x component of c1, which is this way. There's a y component, which is upward. There's a z component, which is at the other angle. A simple example is this. If I am pointing like this on a two-dimensional board, it's got an x component and a y component. But if I point like that, it's got an x component, a y component, and a z component. Get it? So there are three components. What's the connection between C1, U1, V1, and W1? What's the connection? What's the relationship between okay, let me give you a simpler one. On a two-dimensional plane, if something is moving with the velocity c1, it has two components, which is u1 and then v1. What's the relationship between u1 and v1 and c1? v1 square plus u1 square plus v1 square is equal to c1 square. Now apply that for three dimensions as well. So what is the connection between c1, u1, v1, and w1? u1 square plus v1 square plus w1 square is equal to c1 square. You get it?
Could you write that down?
Sure. Do you understand what I said just now?
Yeah.
Like, for example, if I ask you this question, you must have done these things in ACT or geometry. What's the longest pole I can fit into this room? What's the longest pole? Because you said pole vault. Let's talk in terms of that. What's the longest pole we can fit into this room?
Whatever the diagonal distance.
Diagonal. Which diagonal? From there to there. How do you measure it? Like, tell me mathematically, what is it? Yeah. L square plus width square plus height square root. Why? Because what is this length from there to there? That corner to that corner? It is just L square plus height square, right? And then if I'm going to do it on the, like, okay, on the ground it's going to be length square plus width square. And now if I raise it up, So I have this and I have that. You do the Pythagorean theorem again and you get that. So C1 squared is equals to U1 squared plus V1 squared plus W1 squared. Just understand that. Okay? This is the relationship. So this molecule is moving with a momentum of mu1 in that direction. And this molecule is moving in that direction with mv1 momentum. And the same molecule is moving towards towards the other wall with mw1. So it has got three momentums. And the resultant of all the three momentums is mc1. Yeah.
Which one's your Z component?
You can call it anyway. I'm taking that one.
Would you not have to do your X, Y before you add in your Z, or does that not matter?
This is your x component. This is your y component. This is z component.
So you would have to put it in parentheses? Or does it?
What do you mean?
Never mind.
Like, this is the velocity with which it's going to hit this wall, the x wall. This is the velocity with which it's going to hit the y wall, that wall. And this is the velocity with which it's going to hit this wall. Make sense? Like this wall is z. X is this wall, that is your x wall, that's your y wall, and that's a z wall. So if a molecule is moving with a certain momentum, it has got an x component, a y component, and a z component. Understand it on a two-dimensional board, but I think you can do it, right? So now that we have split it into three components, tell me what is the initial momentum of this molecule when it hits this wall? What's the initial momentum? M, wall X. It is M, U1. U1 here. This is the momentum with which it's going to hit this wall. What's the final momentum? You understand? It's mu1. So that's your x wall. It's going and hitting with mu1. What's the final momentum? Negative mu1. So what is the change in momentum? Change is what? What is change defined as? So what is it? Negative mu1 minus mu1, which is negative 2 mu1. That's a change in momentum of the molecule. Yeah.
Why is it negative again?
Because final, what's the final minus initial? Change in momentum is always final momentum minus initial momentum.
No, the final momentum. Why is the final momentum negative?
Because it's bouncing this way.
So we're assuming it just reflects.
Yeah. I mean, I told you that, one of the assumptions is it is not losing kinetic energy, right?
So I mean, like, that it reflects 180 degrees exactly.
Yeah.
Okay.
Because we're taking the x component. Remember, the molecule is actually not going in that direction. We have split it into components for convenience, so that you can discuss on that first and then generalize it later on. So mu1 is the component with which it hits this wall. And mu1, negative mu1 is the component with which it's coming back. And this is the component which is coming back. So what's the change of momentum that it undergoes, that the molecule undergoes? Right? What is force defined as? Force is change of momentum over rate of change of momentum, right? Force. So what is a force experienced by the molecule? It is a change of momentum experienced by the molecule divided by how often it is hitting there, divided by the time. What is this time? It's a time between collisions. So T stands for time between collisions. What do you mean by time between collisions? Look at this. It bounces on this wall, right? It's off. Goes, hits the other wall. Comes back again and hits this wall again. How long it takes for that to happen? So what is the time between collisions on the same wall? Let me see if we can manage this. What's the time taken for the molecule to come back and hit again?
2LU1.
Huh?
2LU1.
Check it out again. Okay, here we go. This is one wall. This is the X wall. This is the minus X wall. Okay? This is the other wall. Well, think of this classroom wall. After one collision there, it's gone. Hits. Comes back again. Hits again. After how long is it hitting again? What do? Total distance over? The time is my question. Divided by velocity. So what is it? That is it. Divided by. Distance divided by speed gives you the time. So 2L is the total distance. Look, after hitting here, it has to go a distance L, come back a distance L to hit again. With what speed? With U1. And so it should take a total time of 2L over U1. And therefore, what is the force on molecule? What's the force on molecule number 1? It is delta P, which is negative 2mu1 over 2L over U1. What's it? Two cancels out. Negative. mu1 square over. This is the force on molecule 1. Now I'm going to ask you another question. What is the force on wall X? This is the force on the molecule. What is the force on the wall? Huh? Same thing but? Same thing but? Positive. Force. The force on the molecule is this way, and therefore the force on the wall should be positive. By the time you finish this kinetic theory, you will actually almost review a lot of material of your kinematics, because that's what you've done. This is the force on molecule 1, which is negative mu1 square over L. Therefore the force on wall X is just the positive of that. So you got the force on wall X. This is the force on wall X by what? By the first molecule only. Now understand that there are so many other molecules. This is moving with velocity C2. That's moving with velocity C3, C4. Like that, there are many. So what is the total force on wall X? Total force on wall X. That will be mu1 square over L plus mu2 square over L plus mu3 square over L, etc., etc. Till mun square over L. There are n of them. So it goes on. mun squared over L. And you can actually now simplify this. So what is the force on wall X? Force on wall X is going to be m over L u1 square plus u2 square, etc., un square. Right, that's what it is. That's a force on wall X. Now, what is the pressure on wall X? What's the pressure on wall X? Just created by all the molecules. How do you find pressure? Pressure. You defined pressure earlier in the last chapters. Force over area. Don't forget all those little fundamentals. Force over area. What's the area of wall X? L squared. The area of wall X is L squared, and therefore pressure on wall X is going to be Fx divided by L squared, and that will get you m u1 square plus u2 square, etc., up to un square divided by L cubed. What is m standing for? Mass of what? Of the molecule. Okay. So this is the pressure on wall X. Yeah.
Why aren't you also squaring m? Oh wait, never mind. I was like, I wrote something down.
I'm going to take this off. Okay. Pressure on wall X is this. So what do you think is the pressure on wall Y? Pressure on wall Y is going to be m over L cubed, but then V1 square plus V2 square, etc., Vn square. So now we are generalizing things. We're generalizing things. What is the pressure on wall Z? It will be m over L cubed W1 square plus W2 square Wn square. That's the pressure on wall Z. Now, statistically speaking, what do you know about Px, Py, and Pz? In other words, the pressure exerted by the molecules on that wall compared to the pressure exerted on that wall compared to the pressure exerted on that wall. Statistically, should be the same. Why? Because the atoms and molecules are kind of distributing themselves. In other words, there's no crowding on one wall only. You understand? Now, if I'm going to take only 10 molecules in this room, I cannot say the pressure is the same everywhere. Why? Because since they're moving in random directions, it's possible that 5 of them are hitting that wall at the same time when nothing is hitting there, right? But if you have millions of atoms, and if they are distributed evenly, the pressure exerted should be approximately the same, very much the same. So since the pressure exerted is the same, Px is equal to Py is equal to Pz is equal to P, the pressure in the container. That's what we're trying to get. The pressure in the container is P. So how do I get P in terms of all of these? The best thing to do is add them all up. Px plus Py plus Pz should be equal to what? 3P. Now, so I'm going to add these things. I'm going to add this with this and with this. I'm going to add them all up. Now, when I'm adding them up, I'm just going to be, so basically what I'm doing is this. M over L cubed U1 square plus U2 square Un square plus M over L cubed V1 square plus V2 square Vn square plus M over L cubed W1 square W2 square Wn square. And this whole thing is supposed to give me 3P. Now I'm going to add in a special way. I'm going to rearrange all this. I'm going to collect this, and this, and write it this way. M over L cubed, opening a big bracket now. I'm collecting U1 square plus V1 square plus W1 square plus, now I'm collecting those, U2 square plus V2 square plus W2 square plus, and the last one is UN square plus Vn square plus Wn square. Make sense? I've just collected them. And what is U1 square plus V1 square plus W1 square? So we are bringing back the velocity C1, which we split for convenience. You understand now the whole idea?
Yeah.
We split C1 into 3 components, and we discussed what's happening on each wall. Now you're bringing it all together. And we want our C1 and C2 and all that back again. So this is now going to be 3P is equal to M over L cubed C1 square plus C2 square, etc., Cn square. I'm going to take that side. Since in our assumptions we said that the molecules undergo elastic collisions, what is conserved? The kinetic energy is conserved, right? The kinetic energy should be conserved. That means what? Although they are moving at different velocities, C1, C2, C3, C4, C5, the average kinetic energy should stay the same, right? So what is the average kinetic energy? The average kinetic energy is going to be half m C1 square plus half m C2 square, etc., half m Cn square divided by, what's the average kinetic energy of each molecule is what I'm trying, by n. And so this becomes half m C1 square plus C2 square, etc., Cn square divided by n. This is the average kinetic energy. So if somebody is asking you, how fast are the molecules moving here? You need to say some speed, right? You have to mention some speed. How fast are the molecules in this room moving? You got to say, all right, they're moving at 400 meters per second. They're moving at 600 meters per second. You know, because you know the average kinetic energy is something. Therefore, they must be moving with a certain speed. But at the same time, you know that they're not moving at the same speed. They're moving at various speeds. So you need to mention some kind of an average. And that is what we say. Average kinetic energy is written as mc, half m, c bar square. This is called the mean square speed. It's called the mean square speed. What do you mean by mean square speed? Mean square speed is C1 square plus C2 square, etc., up to Cn square divided by n. That's called the mean square speed. And so the average kinetic energy is half mc bar square, and the c bar square simply means mean square speed. Okay? Or mean square velocity. Why do we need to focus on this mean square velocity and not just mean velocity? What's the average velocity of all the molecules in this room? What's the average velocity? If I ask you this question, what is the average velocity of all the molecules in this room? 0. Yet there is kinetic energy. So how can you just say, like, how do you relate average velocity with the kinetic energy? The molecules are moving. At the same time, you're saying average velocity is 0 because for every atom or molecule moving that way, there is another one moving that way. And the whole gas is not moving anywhere, right? So the average velocity is 0. At the same time, you know that there is activity going on inside. And how do you measure that activity? Is by this mean square speed. That's why we don't use the term average velocity. Instead, we use the term average square. Yes?
If the AC was going, the kinetic energy still equal to 0? If the AC was blowing in the room?
Pretty much yes. But when the air conditioner is going on, what is the air conditioner doing? It is taking the heat from inside here and kicking it out. So basically, the air conditioner is trying to slow down the molecules, therefore reduce the temperature. It's slowing down the molecules in this room. That's what the basically AC does that. AC's job. We'll talk about AC in the next chapter. Okay, and when you do thermodynamics, we'll talk about that. All right, right now, so what do you understand right now is that C1 square plus C2 square, etc., up to Cn square can be now written simply as NC bar square. So if I tell you the average, the mean square speed in this room is something. If I say the mean square speed is something, you can actually like multiply by the total number of molecules and that's it. You have the total of everything. So I'm going to replace this bracket with that. I'm going to substitute this here. So what will happen to this equation? 3p is equal to m over L cubed n C bar square. And now what is pressure therefore? M n C bar square. Remember, it's not C to the power of -2. It's a little confusing. It's not C to the power of -2. It is C bar square. Mn divided by I'll take this. We're almost reaching our final steps. C bar square is called the mean square speed. So what is C bar? C bar is called root mean square speed. In short, we call it RMS speed. Root mean square, RMS. You'll hear this many times in future. Root mean square speed, RMS speed, RMS speed. Because what is the speed of the molecules in this room is a very stupid question. Because you know that they're going at different speeds. So the statement will be, what is the RMS speed in this room? Right? That is what it is. So how fast are the molecules moving in this room? But the speed that is expected is the RMS speed, not the actual individual speeds. And when I said 400 meters per second, I'm talking about the RMS speed, not individuals. So what is the RMS speed? The RMS speed is the square root of the mean of the squares. It's just a square root of this. So the root mean square speed is simply this. So if you know the velocities of each and every molecule, you just square all of them, divide by n, take the root, and that will be the speed. Now, putting that again, using that again there, P is equal to what is L cubed? Volume. And what is Mn? What is Mn? What is M standing for? Mass of each molecule. What is N standing for? Number of molecules. What is Mn standing for? Total mass of the gas. So it is mass of the gas, C bar square, over 3 times volume. Now what is that? Density. So now pressure in this room is 1/3 density C bar square. That is our climax. The pressure in this room right now, is 1/3 of the density of this air times the root mean square speed. Mean square speed. There it is. So can you tell me how fast are the molecules in this room moving right now? Plug it in. You know the pressure in this room?
No.
No?
0.
What's the pressure in this room? Atmospheric pressure. Substitute. This one is 1.01 times 10 to the power of 5 pascals. Right now the pressure in this room is atmospheric pressure. Equals to 1/3. What's the density of air? Say that again.
Say 1.29.
Exactly. 1.29. Don't hesitate, you know it. 1.29 kilogram per meter cubed. Correct. 1.29 kilogram per meter cubed times C bar square. Can you tell me what is C bar now? That will at least tell you how fast these are moving. 484 meters per second. And it's much faster than speed of sound. So the atoms in this room are now moving with a root mean square speed of this. This is root mean square speed. Although we say that it's moving at 484 meters per second, probably there's not one of them moving at that speed. You understand? 484 is the RMS speed. This is the RMS speed. It is not the individual speed. Individually they are going at different speeds. But the root mean square speed is 484, implies some of them are going slow, maybe 100 meters per second. Some are going 900 meters per second. So the speeds are completely different. Some molecules are not moving at all, temporarily just stagnant, and the other ones are going really fast. So they just exchange their kinetic energies in such a way that this kind of stays the same. Now what is the effect of turning on the air conditioner? The air conditioner will actually try to take away energy from the room. When it takes the energy from the room, the average kinetic energy drops off. Therefore, the root mean square speed comes down. So the root mean square speed of the atmosphere outside in winter is less. In summer, it's more. So the atoms are bumping into you much faster in summer than in winter. You understand? So you get a lot of heat or energy coming into you because they're bumping into you. Yeah.
Is there an equation that relates temperature to
Yeah, we'll be going to that. So do you understand this equation now? This is the pressure in the room, so you can actually figure out. So if I tell you the density of hydrogen in a container, and if I tell you the pressure in that container, can you figure out how fast they're moving? Talking about gas laws. Do you know the gas laws?
expand indefinitely?
No, the laws, ideal gas laws. What are the ideal gas laws? The Boyle's law, Charles' law.
Grams, Henry's, Cohen.
What is that again?
Someone.
Someone?
Great guess.
Yeah, it's easier to call it pressure law because the actual law is called Gay-Lussac's law. Yeah. So Gay and Lussac were two people. So Gay-Lussac's law, but it sounds very difficult, right, to pronounce or to say. People misunderstand. Anyway, Gay-Lussac's law, that's the pressure law. So there are three laws: Boyle's law, Charles' law, and pressure law. We'll be doing that in detail. But you know the gas equation is PV is equal to nRT. Do you know this equation or no? You know that equation, right? We will use this. I will be going through all the laws in detail. So this is PV equal to nRT, where N stands for the number of moles, R stands for the molar gas constant, T stands for the absolute temperature, V stands for the volume, P stands for the pressure.
What does R stand for?
Molar gas constant. I told you I'll be doing that in detail later. So P, you know, is 1/3 rho C bar squared, and rho is mass over volume, and the mass is mn. Right? I'm going backwards now. So if I cross multiply, I get PV is equals to 1/3 mn C bar squared. And that means this nRT is equal to 1/3 mn C bar squared. So we bring in the temperature component, and I will continue with this equation in the next class.